Uh, Thank you so much. I would like to apologize in advance because I got cold and I have sore throat. Uh, so sorry if I couldn't deliver this properly. Uh, yeah, yeah, I'm just gonna go through our geochemical result, which was part of high use pre and high store power project. So within these projects, we are looking to different aspects of geological hydrogen storage. So first project was high store power was funded by UKRI. Then we extended, we got another funding from Horizon 2022 with a larger consortium from Europe, which is led by TNO. So we basically high use pre is the uh, continuation of high store power project. So when we inject hydrogen underground, there are lots of processes happening. Maybe I do my mouse. Do you see my mouse here? My pointer?
Yes, we see it.
Oh, okay. Yeah, so after when we inject hydrogen, so many reactions, so many processes are happening. Especially if we have a cushion gas in place, which might be CO2, natural gas, or nitrogen, it will make it more complex because we will also have mixing zone, and also presence of different gases may initiate different reactions. Upon injection of hydrogen, we will have some um, dissolution of hydrogen in water. Some of it will get absorbed to clay surfaces. Some of it may interact with rock, and if we have microbial community down there, some of them may consume that. Also, there are some other physical reactions. Hydrogen have negative Joule-Thomson, so it will have heating upon injection. But yeah, there's still discussion about that, if the temperature of the injection point will be higher or lower than the reservoir. Also, the injection and withdrawal rate is important to avoid lots of problems such as gravity override or viscous fingering. In the geological hydrogen storage, and like in contrast to CO2, we want to get out as much as hydrogen we can, and we have minimum trapping. So the challenges are in hydrogen storage is a little bit different from CO2 storage. So within these projects, these two projects, we analyze different physical, geochemical, microbial reactions and that could happen during hydrogen injection and withdrawal. We also cover some social aspects and political and economical parts. And then we also use the physical, geochemical, and microbial result to fed into a large scale simulator to do the reservoir simulation. So, but my presentation here will only focus on our geochemical results. So we've made this nice high pressure vessels that we could run high pressure experiments in presence of different rocks and fluids in presence of hydrogen. For running our experiments, we disaggregate our rock samples, then add brine with desired salinity. Then after removal of air, we inject hydrogen and basically cook these rocks under hydrogen at different temperatures and pressures. And we run these experiments from 1 week to a few months. During the experiments, we monitor pressure and temperature change, and after experiments, we analyze the water chemistry and also analyze the gas phase to see any reaction is happening. So far, we have done so many experiments on different sandstones at different temperatures, a wide range of pressures, salinities, different rock size, and different to rock ratios. We have also done experiments on some caprock samples, more caprock samples. We are now doing some more experiments on new caprock samples. We have done experiments on cement samples and with pure minerals as well. Also, now we are doing some experiments when we have impurities in gas phase such as CO2 or natural gas. We realized that temperature, pressure, salinity, like sterilizing samples before experiments, and the amount of rock we put in the experiments, the amount of water we add, how much our rock size, and the material of reaction vessels. Also, if we remove oxygen beforehand or not, or will impact our experiments. Also, we realized that when we add hydrogen, we change the pressure of the system. So some of the reactions could be happening just because of adding hydrogen. That's why we decided to run some control experiments, which is basically we run the experiments in parallel with nitrogen as well, to make sure what we are seeing with hydrogen is directly related to hydrogen, not pressure. So we run the same experiments with nitrogen. Also, we run some other control experiments without any pressure or any gas in the system, to see what we will see if we just put rock and water together. We also have done lots of repeatability experiments and try to make sure what we are seeing is directly related to hydrogen. Here is I'll put a sample of a few sandstones we used in these experiments. For example, these are 4 different sandstones from different parts of UK. Also, we got 6 different samples from rough fields. Here you can see different minerals we had in these sandstone. I just here put, I will not go to exact percentages, just wanted to put here to show you we had different minerals in the system when we run these experiments with different sandstone rocks. After finishing the experiments, we analyzed the water. Initially analyzed the water chemistry. Here, what you see is the concentration of different elements. You can here see the name of elements on top of each figure. Concentration of the elements after experiments. So the red ones is the concentration of elements after hydrogen experiments minus concentration of elements after finishing with nitrogen. So basically, this shows the differences of hydrogen and control experiments. And the gray ones is the concentration of elements after finishing experiments with hydrogen, deducted by the concentration of elements after finishing without any gas in the system. Here you see we have a wide range of changes when we had a pressure change, but when we run the experiments with nitrogen at same pressure, we could see basically hydrogen didn't influence much the chemistry of water. In this article, we also showed that these changes we were seeing is just due to repeatability of just a repeatability error, and is also related to some impurities in the salt. Even though we get research grade salt, but it still has some small ppm level impurities. This showed us, after comparing hydrogen and control experiments, showed us we didn't see any changes in the water chemistry after exposing the system to the hydrogen. We also analyzed the gas phase after finishing the experiments, and the only impurities we saw in the experiments just was water vapor. So this is the composition of the gas phase after finishing experiments with hydrogen, and this is with nitrogen. In both experiments, the only impurities we observed was water vapor. We also monitored the pressure and temperature, and we didn't see any changes in pressure and temperature. So so far what we have concluded, that when we have pure hydrogen, we couldn't find any reactions that's directly related to presence of hydrogen. We run some other experiments, but I should highlight that we did experiments on certain range. So in the range that we did the experiments like pressure, temperature, and salinity. So if we go to some extreme range, for example, at very high temperatures, there are some reactions reported that could happen. We also saw some severe reactions with hydrogen when we had some microbial activities in the system, for example, and when we added some food for the bacteria, we could see very high percentage of H2S in the gas phase, and it could be like up to 1% sometimes. So we published this result in an article recently, which covers most of our experiments with sandstone. So if you like to read more about that, please check this article. This was end of my presentation. Yeah, please let me know if you have questions.